Okay. Hello, everybody. We are doing a mathematical problem with squares of various dimensions.
Okay, that's right.
Okay.
A 1 by 1.
1 by 1.
A 2 by 2.
3 by 3.
And
4 by and a 4 by 4. And there may be a later video of 5 by 5. Maybe a later video of 5 by 5.
Okay. Now the problem is to see how many rectangles you could put in these various squares. Okay. For example, in a 1 by 1, obviously you can only put one square. In a 2 by 2, you can have 1, 2, 3, 4. That's those 4. You could have 1 and 2. That's a rectangle. 1 and 3. 2 and 4. And 3 and 4. Now, if you add all those up, you get a total of 9. And finally, all 4. 1, 2, 3, 4. Yeah. Okay. Now the 3 by 3. The 3 by 3 is a little more complicated. You have the individual squares. There's 9 of those. You have the 2s. I'm not going to put them all in, but like that. And if you do it the way I do it, you start with 1 and look at the squares you can put from 1 that are two squares in length. And then you do the 2, and then the 3. You won't miss any. And there's a total of 12 of those 2s, 6 of the 3s, 4 of the 4s, 4 of the 6s, and 1 of the 9s. All right? And that total adds up to 36. Now, if you continue with the 4s, it gets more complicated. But you do the 1s, there's 16 of those. Then you do the 2s. And the 2s have 24. Then you do the 3s, there's 16. You can do this yourself. The 4s, depending on whether you go in a straight line or in a square, you have 8 and 9. The 6s, you have 12. The 8s, you have 6. The 12s, you have 4. And the 16s, of course, you have 1. You add all those together, you get a grand total of 96. Now, as we saw on the previous video, when you did the one-dimensional arrays, it fit a nice equation, all right? So we're going to see if there's a relationship between the dimension of this square, like this is a fourth, x equals 4 in this, it's 4 by 4. This is a 3 by 3, so x equals 3. X equals 2, x equals 1, and if you had none, x equals 0. So the next, we have the dimension of the square. And for a 0 by 0, of course, you can only have 1, a 0.
Well, this problem will be doing x and y. X equals the
dimension.
The dimension. Like back in this sheet, there's no zeros because
we didn't do the 0.
If we put a 0 in there, it wouldn't be anything. So this could be the 0.
Yeah.
And then you have the 1. So the 1 is that 1. Then the 2 is a 2. And those, well, like that.
Okay.
Then we have 1, 2, 3, 4, and y is the number of rectangles you can make it.
And with 2, we saw there were 9. With 3, was it 36? And with 4, it was 96. Now the question is there a simple mathematical relationship between the dimension of the square and the number of rectangles you can get from it? So let's do a little plot, an XY plot. So in doing that on Excel, it's very simple. I'm going to highlight the X's and the Y's. I'm going to click Insert, and I'm going to do a scatter plot without any line attached to it. All right. This is X on the horizontal axis and Y on the vertical. And I might just put the X and the Y in. Okay, that'll be X. And now let me just quickly do the primary vertical axis. I want to put it.
Didn't you say that? Wait, did you come up with the equation for if it was 94?
I haven't done that yet. I'm going to do that.
Since you said it would be easier if it was 94.
Yeah, I'll show them that. Yeah.
But why did you say that? Why did you say that?
Okay. All right. I'll explain. All right. Now let's get a trend line, and we're going to do a polynomial. So y is going to be equal to x, a function of x. I'm going to do a third order polynomial. So the highest power of x will be the third. I want to set the intercept to 0. I want to set the equation on the line, on the graph, and the r squared value is the correlation coefficient. When r squared is equal to 1, it means it's pretty much a perfect fit. And as you can see, this is my equation. It's a little complicated, but the number of rectangles, y, is equal to 2.164 times the dimension of the square to the third power minus 3.1957 times the dimension of the square squared plus 2.1473 times x. And so we get a good fit, but the coefficients in front of the powers of x are a little complicated. I discovered to my amazement that if this number, instead of being 96, of course it is 96 as far as I can tell, we're 94, you get a simpler relationship for some reason. So let's just redo it with 94. Okay, so I'm going to insert a scatter chart. I'm going to put a trend line with the third dimension, with polynomial of dimension 3, I should say. Set everything to I did before, and you can see now I also get a perfect fit, but the numbers are very simple. The numbers in front of the x cubed is 2, and 2.5 in front of the x squared, and 1.5. So I don't know whether I made a mistake, but as far as I can tell, I haven't. So anyway, there is a simple relationship possible, but there is a relationship possible, but it's not quite as simple as the linear one that we did the other day. Okay, so for Charlie Pepin and Charlie Marzacco, we're going to sign off now.
If there's nothing on
the third sheet.
So we might do one with the third sheet. Right now we only have 2 sheets.
Okay, thank you.
One has 1, 2 has 9, 3 has 36, 4 has 96.
That's as far as we
and this.
That's a mistake.
1 still have 96. And anyways, we don't have the 5
by 5, but it's going to be a large number. I could, if you want, I could show you what it would be predicted to have.
But we can use the equation to find.
Yeah, let's go back to the 96 and see what the equation gives us. All right. Okay, so let's put a 5 here. And then we're going to say equals 2.164 times this number cubed.
You didn't put times.
I didn't put times. Thanks, Charlie.
Times.
This number cubed. I have a feeling it's not going to be an integer. Minus 3.1957 times this number squared, whoops, plus 2.1473 times this number. It'd be interesting to see if it's an integer. No, it isn't. Okay. It would be interesting to do this with the other, if this were 94, to see if that came out to be an integer. Shall we try that?
Yeah, but wouldn't it have to be an integer?
Yeah, it would have to be an integer. I can just try it this way. I put 1, whoops, 0, 1, 2, oh, whoops, 9, 36, 94. And let's just see. Oh, I have to put the 92 in here. Let's see. Let's do it this way. Okay, let's do it. I'm going to make another graph. Insert. I want a scatter. And now I want to do a trend line. I want to do a polynomial of order 3. It's very curious. See how nice it comes? All right, now let me see what I get for 5 here. So it equal 2 times x cubed minus 2.5. It may not be, I won't get an integer here either. There's nothing to guarantee that it has to be a simple relationship. Squared plus 1.5 times x. Okay, the moment of truth is here. Does it look right, Charlie? It is an integer. It is an integer, 195. It makes me feel like I made a mistake. It should be 94 instead of 96, but I checked it and checked it and checked it. Well, we'll keep checking. And anyway, it's an interesting little problem. The next step would, we've done a one-dimensional array. We've done a two-dimensional array. A three-dimensional array is kind of hard. You got to do a 0 is 0, a 1 would be 1, and then a 2 by 2 by 2. It's 2 blocks in the x direction, 2 blocks in the y, and 2 blocks in the z. Thank you for your attention, and we'll see you next time.